Okay, good morning. So today I'm going to talk about a little bit more about work done by non-conservative forces, just to give you some, refresher on that, and we'll talk about power. So remember that work is equal to delta KE, right? So we can break this work up into work done by different kinds of forces. We can look at, the work done by gravity, the work done by friction, and we break it up into work done by conservative forces and work done by non-conservative forces. So we can write it, I'll just write it as WC plus the work done by a non-conservative force is equal to delta KE, okay? That work done by a non-conservative force for us is friction, and it's negative. So it's actually taking energy away from the system, okay? In other words, let's say you have an object that is sliding along a flat surface. Here's an applied force, and here's the force of friction, kinetic friction, okay? And you slide the object through some distance, delta R, all right? So it goes through some short distance delta R, some distance delta R, and the work done, the net work, is FA minus FK times delta R, and that is equal to delta KE, okay? This is the net force acting on the system. I'm ignoring the gravitational force, I'm ignoring the normal force. So this, let me write it up here. Okay. So this is equal to FA delta R minus FK delta R, and that equals delta KE. Okay? That is the work done by kinetic friction. This is something negative. If there were only the work done by the applied force, like we talked about when we were doing problems without friction, this would be just the work done without friction, okay? So this is taking energy away from the system. This is adding energy to the system. This is doing a positive amount of work. This is doing a negative amount of work. And we can look at the work done by this non-conservative force, and that's simply the work done by the non-conservative force is minus FK delta R, okay? So when you're working these problems and you're looking at forces that are opposite to the direction of motion, like the friction force, they're doing a negative amount of work. You already know that if the force is in this direction and the displacement is in this direction, then you are doing a negative amount of work, okay? So we did some examples on that, and I'm not going to do any examples right now, but I'm going to give you some homework to do from chapter 7 and chapter 8, and hopefully you'll work on it over the weekend and we can talk about it next week, okay? I want to talk about power. Power. So what is power? Power is related to work. It is the amount of work divided by the time that it takes to do that amount of work. So it is the time rate or well, let me show you. It is the work divided by time. Okay? This is equal to P for power. Okay? So it's not how much work you did, it's how fast you did the work. Let's say that you and your friend are going to climb a set of stairs. You climb a set of stairs in 5 seconds, okay? You've increased your potential energy by a certain amount. You've done a certain amount of work. You have some gravitational potential energy, and it took you 5 seconds to do that amount of work. Let's say your friend climbs the stairs and it takes them 10 seconds, okay? They did the same amount of work. They're at the top of the stairs. They've got the same potential energy that you do, except it took them twice as long. Your power was greater. The denominator here was less than the denominator for your friend, okay? So it's the amount of work divided by the time it takes to do that work. This would be average power here, okay? So if we look at the instantaneous power, power is equal to dW dt. The instantaneous power is how much power is being used at a particular instant, okay? And you can do some calculus on this, which I'm not going to do, but this is equal to F dot V, okay? So if you have a force that you're interested in, how much power is being generated by this force, then you take that force, you take the dot product with the velocity of the object, and that gives you the power, that's the instantaneous power for that particular force, okay? Power is in watts. That's the SI unit for power. A watt is a joule per second, okay? A watt is a joule per second. So just like I said, it is work divided by time. All right, so let's look at a little simple example. I'll use an example from electricity, but when we do the problems, and we'll talk about the problems as far as what we're going to do with mechanics and power. But just to give you a feel for the idea of power, does the utility company charge you for power, or do they charge you for energy? Well, they charge you for energy. The energy that you use is calculated by the power that you consumed multiplied by the time that it takes for you to consume that power. So, most of you have a hair dryer. Let's say it is a 1500 watt. Most of these are rated at 1500 watts. So that's 1.5 kilowatts. And that 1500 watts, let's say that you take a half hour to dry your hair, okay? So 1500 watts times a half hour, that's going to be a unit of energy. Okay? That's going to be something in that's going to be in watt hours. The utility company charges you for power or energy in kilowatt hours. So this is 1.5 kilowatts times 0.5 hours. And I think that is 0.75 kilowatt hours. Okay? So that's 0.75 kilowatt hours. Now, how much does the utility company charge you for power? Well, I don't know, around here maybe about 7 cents per kilowatt hour. So the rate, it's 0.07 per kilowatt hour. Okay. So how much does it cost you to run your hairdryer for 30 minutes? Okay. So I don't have you guys here to do the calculation for me, so let me look at this. 0.07 and we've got 0.75 kilowatt hours. So that cost you about 5.25 cents. Okay, so that costs you 0.0525 dollars, which is equal to 5.25 cents. Okay. So this is the idea of the relationship between power and energy. You can consume this much power in a given amount of time, and that gives you how much energy was used or consumed. Okay? In our case, when you're talking about something mechanical, then you're looking at a force through a distance that gives you the work done by that force, or you're looking at a force times a velocity that gives you the power that that force is consuming or being applied, or wherever that energy is coming from or going to. Okay, so this is a pretty little short lecture. It's the first one that I've done, the first one that I'm going to post. So what I'll do next is I'm going to go ahead and give you some homework problems. And next time I post a lecture, I will start going through those homework problems and helping you with those. And we'll get through 7 and 8. We'll have to do chapter 9, which is momentum, collisions, all that good stuff. And we'll do a little bit on gravitation. We'll probably shorten that. But I think we're okay on time. I think we have plenty of time to do the things that we need to do. So I appreciate it. I know this was short, but it's sort of a startup kind of lecture now that I've got everything set up. And I'll see you guys soon.